All right, so to that I would recommend bumping this guy up real quick, expressing it as a negative exponent. We now have done derivatives where you subtract, antiderivatives you're adding. So it's just easier to kind of see that by rewriting it. So you're going to get x to the negative 1. You're going to divide by a negative 1. We're going to evaluate from negative 2 to 2. Let me rewrite this so that it looks like a negative 1 over x from a negative 2 over 2. And then throw in your limit. So I'm going to get a negative 1 over a2 minus a negative 1 over a negative 2. There's a lot there. So what's that? Really a positive 1/2. So we should get negative half minus a half. We would get a negative 1 for that answer. All right, we all good with that? Here's where this gets tricky. Let's go to our calculator and let's do a quick little math 9 on this guy. So what did I give you? Negative 2 to 2. Oops, forgot the 2. So I go negative 2 to 2. And then we integrate 1, actually, over x squared. And then see what your calculator tells you. Because calculator never lies, right? Calculator's always right. It's infallible. We're humans, we make mistakes. Calculators obviously never make a mistake. So when we throw that into our calculator, does it give us a negative 1 for those plugging that in right now? No. In fact, it argues with you a little bit, right? It tells you that there is an error, and it says this weird thing about dividing by 0. So here's where this gets a little sneaky. Some of these are really obvious. Some of them are a little bit trickier. The problem that I gave you when I tell you to do this by hand, we can all put our head down, grab our pencil, do that problem, thinking that we're doing this correctly, and you're going to get a numerical value for this. When in reality, this is not your final answer. This is not your answer at all. Okay, negative 1 is not our answer. The calculator is right in the sense that we have a problem. Here's why we have a problem. Think about what this graph looks like. In particular, even if you don't know what it looks like, I'll graph it for you here in a minute. But don't we have an excluded value in that function at the x value of 0? Remember what integration means. We're finding the area, that's what the integral means, underneath this curve. Well, don't we have a vertical asymptote at x equals 0? So if we were to graph this, so if we graph this, notice up here at the x value of 0, does my blue graph ever actually hit the y-axis to close that off and give us a finite amount of space? No. So that's our problem. That's not an enclosed region. So if we're trying to find the area underneath this curve, same thing if I try to do this the other way that I showed you. If I try to say we're going to integrate, so if I do number 7, and let's say from a negative 2, it's going to set the bound right here to a positive 2, and it's not going to allow us to do that because it can't find the area around 0 because it's not enclosed. So then the question is, what does that mean? So big picture understanding is what you need to be very, very careful of. There's 2 different ways that we can get what we call an improper integral. One of them is, this is what letter A says down here, the integrand, so this 1 over x squared function becomes undefined at 1 or more points in the interval of integration. So if you notice, I wanted you to find the area between a negative 2 and 2. Since our function was undefined at 0, that's a problem. At least what we currently know, that is a problem. If I were to set that exact same problem up from a negative 2 to negative 1, we're fine, because while 0 is undefined, we're not finding the area at 0. We're good between a negative 2 and a negative 1. So as you look at these, a lot of these are going to look like normal problems. Like this one looks like a normal, regular old problem. This one here is the one we just did. We'll talk about how can we actually do this here in a little bit. This one looks like a regular problem. Some will be, so here's the second way. Notice how there's an infinity in the limit. That should look weird. All right, that's definitely obviously now what we're dealing with here, an indefinite integral. So the ones you just want to be careful of identifying is when your integral becomes undefined within those limits. So that's number 1. So make sure we know that ultimately when we look back at this, that's not your answer. We're going to do that problem here in a minute and kind of show what the real value is. The other way is easy to identify. It's what I talked about here. If you have an infinity in your limits. So think about what that now means. Think about this as the line y equals x, right? and I want you to find the area from 2 forever. Think about what that means if this line goes on forever and I'm going to be accumulating area forever, all right, because that's what we're going to talk about here in a minute. What's happening to the amount of area that we are accumulating? When did that be getting bigger and bigger and bigger and bigger and bigger? Okay, so that's what leads us into these ideas. So the convergence versus the divergence. So convergence, actually write this integral under the divergence one. So actually put this 2 to infinity right here with the x and the dx, and then go ahead and sketch in what this would roughly look like. So what divergence means is basically our value just continues to get larger and larger and larger and larger. That pretty much means we can't do the problem. So when we say one of these integrals diverges, it just means it doesn't have a finite amount of space. That space continues to grow unbounded. This will be a legitimate answer for a number of our problems. We're going to basically say that the integral diverges, right? Meaning the area can't be found. However, let's say we talk about converging. So what I want you to draw in here, and we'll do this one here in a minute. So write an integral for, let's say, 1 to infinity. And let's use 1 over x squared. We'll do this problem in a little bit. 1 over x squared, we have this part down here. You don't necessarily need this one just because of the limits that I gave you. But we do have one that looks like, on the right-hand side, that looks like this. Think about when we did our limits as x goes to infinity. Would we all agree that we have, if I find the limit of this function right here, the bigger degree is on the bottom? So our limit is 0. So do we agree that this guy's got to level off towards 0? So what might happen is, over in time, by the time we're over here at however many zeros I want to add, all right, 1 billion at the x value of 1 trillion, wouldn't this guy be so right on top of the x-axis that it becomes almost impossible to accumulate area? So while they never technically touch, that area or that space becomes so infinitesimally small that we might still approach a limiting value to where we can conclude that limiting value is our area. So some of these, even though it's not an enclosed space, may converge to a certain value. That is what we would then assume is the area of that curve. Okay? So to do these, go to number 1. The first and biggest issue is going to be, especially when you look at number 1, is our first step here, is actually determining if this integral is in fact improper. We never really had to worry about this before. So what that means is, if I look down here and we look at our limits, do the 0, the 1, or any x value in between 0 and 1 cause a problem that would make this function undefined? All right? Yeah, and the answer is, right, 1. All right, so a couple people say that online there. So 1 is a problem. So the way you're going to set this up is, what we're going to be doing is we're going to be evaluating from 0, and then whatever the problem is, in this case it's a 1, we're going to use a variable. Usually it's an A or a B. I like B. And we're going to still integrate this normally, so we're still going to have the same function, 1 over 1 minus x squared. And we're going to do this without this being a problem. Because again, doesn't 1 make this undefined? If 1 makes it undefined, what we really want to then figure out is, do we approach, think about what converging would mean. This basically means we're going to have a limiting value that we would eventually approach. Here our limit doesn't exist. What we want to figure out, since we can't actually let x be a 1, we would want to say, all right, since I can't be 1, it's kind of like my 7-year-old right now. He can't do something or he gets in trouble. He's going to walk that line. He's going to get as close as possible to making me flip out. And then just before he makes me flip out, all right, that's our answer. So that's what we're going to be doing. We're going to get as close to 1 as we possibly can and see if that approaches some limiting value. So when you set these up, and you're going to get an AP question on this too, just so you can kind of get this format and know this will be tomorrow night. So you can kind of know the formatting of this. When they see your work, you have to replace the problem with a variable, either A or B, have to. You then have to show this step here where you're now going to be finding the limit of this integral as we get really, really close to the problem. So in our next step now, leave this guy here. Don't let him disappear. we're going to do what we would normally do. So the antiderivative of this is an old one, intentionally kind of make us remember some of this stuff. So we remember some old antiderivatives. That's the derivative of inverse sine, if you remember that. So the antiderivative of this is the inverse sine of x. We're going to evaluate this from 0 to b. And then just continue to do what you normally do. Plug in your upper limit, subtract, plug in your lower limit. The second part we can evaluate, right? Like the inverse sine of 0 is just asking us on the unit circle what angle has a y coordinate of 0, and that would be the angle 0. So we know we're going to have a minus 0 for this one. And then this is an old limit idea. So all of our old limit rules are going to come back, at least a number of them. What we now need to calculate is what happens as this b gets closer and closer and closer to 1. So as this guy gets closer and closer and closer to 1, what would happen to the overall inverse sine value as we get closer and closer to 1? So your old limit rules, the first rule that we talked about with limits is basically substitution. All right. Nothing is stopping us from doing that in this particular problem. So if my b gets closer and closer and closer to 1, then shouldn't this start to behave more and more and more like the inverse sine of 1? The inverse sine of 1 is asking us, what angle do I have a y coordinate of 1? So that's got to be up here. So wouldn't the inverse sine value be getting closer and closer and closer to pi over 2? Now, we never get there. That's what we converge upon. So with these, you're expected to say this converges to the value of pi over 2. That would be how we present that answer. We never hit pi over 2 because that area is undefined at 1, but that would appear to be what we get closer and closer and closer to. That then would have to be what it actually would equal. All right. So this one converges, this one actually works, even though if you try to plug this into your calculator right now, it's going to give you that same argument that we got the first time. All right, so now number 2. Actually, go to number 3 next. Let's do number 3 next, and then we'll do number 2. 2 is the one that we started the class with, and we'll talk about how we can actually now do that one. So with this one is now easy to identify. This is the opposite problem, where you have your infinity here. Same exact process. Infinity is not a number, so we can't evaluate a definite integral. A definite integral means we have finite numbers. We don't have a finite number here. So that's going to be our b. And what we're instead going to do is evaluate this integral as a limit. What happens, what value do we approach as our b gets larger and larger and larger and larger? Simple antiderivative here. That gives us that natural log absolute value of x from a 1 to a b. Plug in upper minus lower. Like this. And we now know that we're definitely going to get a minus 0 because the natural log of 1 is a 0. And then the question would then depend upon what happens here. So what happens as our b goes to infinity? This is a really common one. You're going to want to recall what the natural log curve looks like. So you did it last year. We talked about it this year. You may or may not remember it. You're going to want to remember it for this section. Here's what the natural log curve looks like. It increases pretty quickly until 1, and then he kind of flattens out like this. So what this question is now asking, as your b behaves more and more like infinity, so as my b gets larger and larger and larger, so as I go further and further and further, you guys can't see that in here, can you? There we go. You still can. What's going on here? So as we go further and further and further, make this smaller, on the x-axis to the right. There we go. So as I go further and further and further, that's what b going to infinity means. It's ultimately your x. What functional value does the natural log curve level off towards, if any? What does it approach the overall y value, if it approaches anything? Remember, we talked about the natural log curve. It does it very, very slowly, but it does get bigger and bigger and bigger and bigger and bigger. It does go to infinity. So overall then, if my b continues to take us further and further right, the natural log value then overall is going to go to infinity. Okay, the overall value also diverges. So in this case, we would say that this one then diverges. The area just gets bigger and bigger and bigger. Let me show you, because this is some weird stuff here. Let me show you this on the calculator. This one isn't the weird one. But if I graph, let me go down here, and let's get rid of the squared. Here's what this graph looks like. What limits did I give you? 1 to infinity? So let me start at the x value of 0. I definitely don't want my y max to be that big. Let's go further on the x-axis. So what that is saying is, if I started at the x value of 2 right here, notice how this never gets leveled off. It's saying our area is going to continue to accumulate. Even though this gets really, 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 really close, since we don't close that area off, our value will continue to get larger and larger and larger and larger and larger. The area grows unbounded. Okay? That's what that means graphically. However, go to number 4 next. Let me show you what this graph looks like before we even do it. So here's what the current one looked like, the one that we just did. Now let me go down here and graph x squared. X squared. All right, do we agree that looks pretty darn similar? So we may be led to believe right now that this is going to diverge as well, because those will never touch. So let's go to this guy. So same process, set up your integral first, get into the good habit of doing 1 to b, whatever our problem is, replace it with a variable. And then we ultimately want the limit as b approaches whatever our problem is. In this case, we want b to approach the infinity. We just did this antiderivative, although I guess I rewrote it. We'll go ahead and rewrite it. So we just did this antiderivative. So if you wanted to cheat, not even, oh no, we didn't. We did it on the previous problem. So let's go through this. This would be x to the -1 over -1 from 1 to b. So this is a -1 over x from 1 to b. So we get -1 over b minus a -1 over 1. Certain right's slanted there. We know this is going to be a +1 at the back end. So what we now need to identify is what happens here. So now think about this old limit idea, or just some number sense as well. If I have 1 and my denominator becomes a 10 and then 10, 100, a billion, what should be happening to this overall value right here if I do a -1 over 10 billion? Does that converge upon a certain value? Does that become something? Yeah. Shouldn't that be getting smaller and smaller and smaller? So overall, that approaches a 0. It's an old limit rule as well. The bigger degree is in your denominator. And when we go to an x value of infinity, if the bigger degree is in our denominator, it's 0. So what that shows us is that this will converge to 0 here. So that overall, even though those graphs looked similar, and that graph never touches the x-axis, so let's revisit the graph here. This graph will never touch the x-axis to close it off. It gets to that x-axis so quickly that we can't accumulate any more area, that the area is just a 1. We would conclude that it converges to a 1. All right. Okay, now we keep avoiding number 2, but this is the problem at the beginning of the class. So now let's see what the real answer is here. When we did it by hand, we got a -1. The calculator argued with us. So now we'll do this officially. The reason I kind of wait for this one is because this one has a little extra layer to it. Notice how the 0 is our problem. And notice how 0 is not the upper or the lower limit. It's in between. So when that's the case, we're going to set up 2 different integrals. for this. As you do it, go ahead and write this as x to the negative 2, just for the sake of the derivative. So these are the ones that require a little bit more work because the x value that's the problem is between the limits. It's not one of the limits. Then what we need to do, I'm going to erase just because I'm lazy, and put this as your variable. So I'm going to say this is our b here. B is going to be the 0. When we figure out these limits now, think about what's happening. We have a vertical asymptote at x equals 0. So this first one, we're going to want to figure out what happens as we approach from the left-hand side of b, right? We're to the left. So the limit that you're going to set up is the limit as b approaches 0 from the left. Oh, my writing's so small here, I can blow this up real quick. There. If I'm over here at the asymptote to 2, what we're going to be finding in this one is what happens as we approach that b value of 0 from the ring. Here's what we're hoping. If one of these diverges, you don't have to worry about the other. As soon as the other one diverges, it doesn't matter if the one has a sum of 2. It would still be an infinity plus 2, and it's overall going to be diverging. So when we do these, we're only going to do one of them. You're crossing your fingers, it just doesn't work, and then we don't have to worry about the other one. So as we go through this first one, we'll do the one on the left, the limit as we approach the 0 from the left. This would give me x to the negative 1 over negative 1 from a negative 2 to b. So I'm going to get a negative 1 over x from a negative 2 to b. So we get negative 1 over b minus a negative 1 over negative 2. The negative 1 over the negative 2 give this a positive 1/2. So we know we're going to be subtracting 1/2. And then what we now need to do is evaluate this limit. And I forgot the left-hand limit here. So this is a really old idea. We just did that cumulative assignment though, so hopefully limits are somewhat fresh in our heads. We now need to evaluate this limit. So what happens to a negative 1 over b as we get really, really close to the b value of 0 from the left-hand side? So this now, our first option with limits is to substitute. If we didn't substitute, the next thing was try to factor and then substitute. That doesn't do us any good. The third idea was the little XY chart. So what that means is think about in terms of x, y. We want to get really close to 0 from the left-hand side. So if I did negative 0.1, think about what a negative 1 divided by a negative 0.1 equals. Notice how that's a positive 10. If I get even closer, negative 0.01, so now I have a negative 1 divided by a negative 0.01. Notice how now I'm at a positive 100. So as we get really, really close to 0 from the left, if we look at this and just follow this pattern, hopefully we would then understand that overall, this function is going to be getting larger and larger and larger, going off to positive infinity. Because of that, it doesn't matter that I now have infinity minus 1/2. That still grows to infinity. So this guy would then diverge. We don't have to worry about what happens with the other one. This overall, that number is getting larger and larger and larger and larger and larger. Okay? We did that one. So did we do 5? No. So number 5, same thing. That's kind of why I wanted to do 2 right before number 5, because it's another one where if we look and identify where's our problem, the x value of 1 is our problem. 1 lies in between these. So this is another one then, just like the one we just did, where you're going to have to set up 2 different integrals. One going from 0 to 1. As we rewrite, let's rewrite this as we do it. So this would be x minus 1 to the negative 1/3. And then the next one would go from 1 to 2, also x minus 1 to the negative 1/3. If you want to rewrite it, go ahead. I'm going to use my eraser, and instead of 1, we're going to replace those with our letter, our variable. When we go to set up our limits then, the first one we would be approaching the value of 1 from the left. The second one, we're going to approach that b value of 1 from the right. And again, hopefully we don't even get to that part. Hopefully the first one fails, we're done, and we can move along. Something I want to talk about here. This technically, kind of like what we did with, and we weren't in class that day, I left it for the video. This is technically a U substitution problem. Unless you just have x to the negative 1/3, where you can do x to the 2/3 divided by 2/3. As soon as it's not an x anymore, you're technically supposed to do U substitution. We don't have to do U substitution though in this problem because, and this is a rule we just kind of want to know to make our lives easier, if we let u be an x minus a 1, as long as your derivative simply gives you a 1, that means we don't really need to do U substitution with this. The regular old power rule is going to work. We don't get anything extra from this. So we can just go ahead and say this will be x minus 1, add 1 to the power, so 2/3. We want to divide by that power, so that's the same as multiplying by the reciprocal of 2/3. And then we're going to evaluate that over the interval of 0 to b. Whatever that gives us, we want to calculate our limit as b approaches 1 from the left. Substitute those in, upper minus lower. So I'm going to get b minus 1 to the 2/3 minus 0 minus 1 to the 2/3. I have a feeling I wrote too big. This one here, understand our exponents. This is the cubed root of a negative 1 squared. So a negative 1 squared is a positive 1. I would be taking the cubed root of a positive 1. So this works out nicely to be just a minus 1. And then now just think, first option is substitution, right? So if I just took the x value of 1 and plug it in for b, so basically 0.999999, isn't that really just 0 to the 2/3 power? So that, unfortunately, somewhat unfortunately, means that this converges. And we'd still have that 3/2 out. So what that one converges to is a negative 3/2. So bad news with that is we still got a second part of this problem then that we now need to finish off because that one worked. So now this one, we want to figure out what happens as we approach the one from the right-hand side. We already know our antiderivative, so that's easy. It's 3/2 x minus 1 to the 2/3. But now we're going to go from b to 2. Plug in your upper and your lower. So we get 2 minus 1 to the 2/3. Oh boy, squeeze this guy in there. B minus 1. Can you guys even see that in here? Nope. To the 2/3. So plug those in. Make this a little smaller so we can see it on the screen. Not yet. And then see what that gives us. Yeah, I don't think I'm going to make it small enough. So what we should have happen, 2 minus 1 is going to be a 1. So we're going to have 3/2 times the first upper limit gives us a 1. And then now just think, if this b is going to become a 1, then this would become closer and closer to 1 minus a 1. So that this gives us a 0. So then that one converges to 3/2. This is somewhat anticlimactic when all of that happens, and then all we end up saying is this converges to 0. Okay? It's a lot of work to get a 0 there. All right, then the two big ones. 6 in particular. In the later chapter, our last chapter, this is gonna get revisited. Pretty straightforward in the sense that we know the upper limit is our problem. So that's gonna be your B, and we're gonna figure out what happens as we get bigger and bigger and bigger for the B. See if you remember what to do with that antiderivative. See if you remember this one. We're revisiting some old antiderivatives today. See if you know what this one is. Anybody remember that one? That's one we can actually just say right away. We don't have to rewrite negative exponents. We don't have to do any power rules, anything like that. Nobody remembers that guy. Remember the inverse sines derivative is 1 over root 1 minus x squared. We did that today. Remember the inverse tangents derivative was 1 over 1 plus the u squared. Isn't this what we have right now? So this guy is ready to go. That is the derivative of inverse tangent of x. We're going to evaluate that over the limits of 0 to b. So I'm going to do the upper limit minus my lower limit. On the unit circle, at the angle 0, that's when the tangent has a value of 0. So we know that's going to be a 0. And then now I'd be very, very happy and impressed if we remembered this. So, because we drew this, we have it in our notes from a long time ago. Think about what happens as my b gets bigger and bigger and bigger. So as the x values move further and further right. So if we think about what the inverse tangent graph looks like, as we go further and further and further and further right on the x-axis, what does our inverse tangent graph do? Anybody want to be just the shining star right now? Remember this. Carter, you think you got it, bud? What do you got? It's not the root 2 over 2s or root 2, but the idea of like the graph and flipping it and redoing it, that is how we do it. Yeah, what'd you say? I thought you just said it, Carter. I thought you just said it. You might have. Let's talk about it. Good. Is that Mo? Yeah. It should be going to pi over 2. Here is why. Remember, we drew the tangent graph when we did this. Here's what the tangent graph looks like. And remember how we have all these asymptotes? But to have an inverse, it has to be 1 to 1. So we only worried about that. The asymptotes on this occur at pi over 2 and at a negative pi over 2. And then remember how we talked about how a function and its inverse will always reflect around the line y equals x. Or let's approach it this way. This is probably quicker since we're running out of time. The domain of the tangent is negative pi over 2 to pi over 2, because that's where you have your asymptotes. Look at the range of the tangent. Doesn't it go left and right forever? Or I'm sorry, up and down forever? Well, the inverse tangent, doesn't that have to be x's and y's get flip-flopped with our inverses? So now the domain should be the range. So the inverse tangent graph should go left and right forever. And the range has to be your domain, negative pi over 2 to pi over 2. So when we drew that in, the way the inverse tangent graph looks like is this, if I reflect this. This is our inverse tangent graph. What we rotate around is, or what we approach is pi over 2. You will want to get that down. Really, really common question. When we get into the last chapter of the year, we're going to revisit all of this, and that's going to be one that you're going to want to know. So this guy converges to pi over 2. Okay, we rushed through that. If we need to revisit that tomorrow, we can. We'll do number 7 tomorrow. I have a quiz scheduled for tomorrow on this. We're not going to do that. All right, so I wouldn't freak out. So come tomorrow, we'll finish up 6. We'll talk about that if we need to revisit, and then 7 we'll hit on, and then we'll, go further from there. Okay? All right, we're good. Have a good night.